Hello and welcome to a video on polynomial functions, and this is an introductory video that focuses on one of the most important terms in the polynomial function, which is the leading term. So first of all, what is the leading term? Well, the leading term is the highest degree term of the polynomial. So this assumes that the polynomial is already in polynomial form as opposed to being in factored form, and the leading term is the highest degree term. Okay, and since we like to put our polynomials in descending order with the highest degree term first, that would make it the first term. Okay, so what is a turning point? Just a little basic terminology here. So the leading term is going to tell us about the turning point. It's also going to tell us about the end behavior. So what exactly is a turning point? And a turning point is just really a local max or a local min. And so if you think about it, whenever, let's say you have a parabola, and this would be like a local min right here, whenever the function is decreasing, hits the local min, all of a sudden it changes direction. It's a turning point. It changes direction from decreasing to increasing. So that's why the local mins and local maxes also work the same way. So what is end behavior? So end behavior is what we're looking at as the function, as x gets very large towards positive infinity or gets very small towards negative infinity. Okay, so we could just write that as it's what a function looks like as x approaches positive infinity and as x approaches negative infinity. And specifically, when I say what a function looks like, we're going to be looking at what's f of x doing. Is f of x going up as x goes to the right, or is f of x going down? And so on. All right, so let's take a look at some functions. The first function that you're looking at is already in polynomial form, but it's not quite written in descending order. So let's first write this in descending order. So this, another way of writing this would be f of x equals negative x to the third plus 1. Notice that negative x stayed negative. So the leading term is just negative x to the third. That's all we're asking here. We'll analyze this once we know how to find it. All right, so that was pretty easy to find because it's already in polynomial form. Now this one could take a little bit of work, but I'm going to show you a shortcut. So here's the long way first of all. The long way to find the first term would be to convert this function into polynomial form by multiplying it out. Okay, and now that we're looking at the function in polynomial form, we can see right there is the first term. It's 2x to the cube, to the third. So 2x to the third is our answer. But, and here's something important, we didn't have to do that. Because when we get to something like this, we're really not going to want to do it. We're not going to want to multiply this whole thing out and put it into polynomial form. And especially when we get to even longer ones, like you don't want to multiply x minus 2 times itself 4 times. It just takes a long time. So here's a shortcut. And I call this collapsing the polynomial. And when I say collapsing it, I'm talking about collapsing away these terms here. Anything that's being added or subtracted to x, all that that's doing is giving us terms other than the first term. The first term just comes from the x's. So when I say collapse, what I mean is to rewrite this as just 2x, I'm just collapsing away that minus 5, times x, and that's going to give me the 2x, oh, I lost something there, what happened? I don't know why I wrote to the third, it's squared. So this is squared, squared, and squared. Okay, so that's my leading term is 2x squared. You probably were watching this thinking, where did that come from? But it's not supposed to be a third degree. It's supposed to be a second degree. 2x times x is 2x squared. All right, so that's what this is, 2x squared. It's actually a lot easier to do and not make a mistake if you do it by just collapsing. Okay, so we're going to look at that method. All we're doing is collapsing away everything that's added and subtracted to get that first term. So let's try it for part C. Let's collapse away. Now this negative 5 is being multiplied, so I'm not going to get rid of that. I need that. I'm going to collapse away that. I'm going to collapse away that. So those are just going to disappear. So I'm going to rethink this as negative 5x, and this is not the whole polynomial, but this will definitely give me the first term, times just x, and this one is x to the third, so just times x to the third. Now I just multiply that out. Negative 5, x to the first, second, plus third, that's fifth, right? We add the exponents. So this is negative 5x to the fifth, and there's the first term. Much, much easier than multiplying this all out. You really don't want to do that. All right, let's look at the next one and try the same thing. Okay, so again, we only can collapse what's being added or subtracted. So I'm not going to touch that. I'm leaving that there. But I'm going to collapse this away. I'm going to collapse this away, and I'm going to collapse that. Those are just going to disappear because I'm only worried about the first term. So I have negative x times just 2x here times 5x times 3x. And when you multiply all of the numbers, you get negative 30 and x to the first, another first, another first, and another first. So that's just x to the fourth. So this is negative 30 x to the fourth. Collapsing the terms. Okay, try this one. I'll pause the video, see if you can collapse the terms and get the right answer. Okay, there it is, x to the 10th. All right, so how is the leading term related to turning points? Now, of the two things that we're going to focus on here, one of them being turning points and the other one being end behavior, the more important one is really end behavior. But we can still get some information about turning points. We can't get quite as clear of a picture from turning points as we can get from end behavior. But this is really important. This really gives you a lot of information about the shape of the graph. But we still need to be able to answer that. So how is the leading term related to the turning points? And if the degree is n, then there can't be more than n minus 1 turning points. So this one can't have more than 9 turning points. This one can't have more than 4. This one is just a parabola, second degree, can't have more than 1 turning point, and we know that it has exactly 1. This one can't have more than 2. So this one, for example, third degree is kind of easy to show this, could look like a cubic like that, okay, or it could look like a cubic with a bump like that, and there's the 2 turning points that it could potentially have. Third degree, 2 turning points. Okay, so in a polynomial function of degree n, there are at most n minus 1 turning points. Okay, and that works the other way too. So if we're looking at a polynomial function and we see the graph and it's got a bunch of turning points, we can conclude something about m. So if there's n turning points, then there can be one more than that for the degree of the polynomial function. Okay, so if the graph of a polynomial function has m plus 1 turning points, then we know that the degree is at least m plus 1. So in other words, let's say I'm looking at a polynomial function that looks like this. Okay, there's a polynomial function. There's 1, 2, 3, 4 local max mins. Those are 4 turning points. I know that this is at least a 5th degree polynomial function. Okay? All right, so let's look at the functions above as we've kind of already talked through these, and what is the maximum number of turning points of the polynomial functions in example 1. So I just want each of these A, B, C, D, E correspond with these. So I'm going to pause the video, see if you can answer those. Okay, so there you go. Now it's important to keep in mind this is not the number of turning points in the function. So we are looking at these equations and we don't know the number of turning points. We know the maximum number of turning points. Okay, sometimes we know, if in the case of a parabola, yeah, we know that that's got 1. So this is the maximum, but it's also the actual number. But in the case of a 5th degree or a 3rd degree, we don't really know that there's 2 turning points. There could be none. Okay, so it's not an absolute. That's why I said the turning point is not quite as valuable as the end behavior. But let's still take a look at this question. So now we're looking at a graph that has 3 turning points. So let's just kind of make one. Let's make a graph that has 3 turning points. So here's 1, 2, and then that's 1, 2. Now if it comes back down, that's 3 turning points, right? There's a graph with 1, 2, 3 turning points. That's at least 4th degree, at least 3 plus 1. So at least 4th degree. Okay, so let's look at end behavior. Okay, as we've already discussed, what does the leading term tell us about end behavior? Well, it tells us whether f of x is increasing or decreasing as x goes towards positive or negative infinity. Remember, it's called end behavior. We're talking about the ends of the function, and even though they never technically end, when I say the ends of the function, I mean as opposed to like the middle part of the function. So things that are far away from the origin, eventually it's going to follow the end behavior pattern. Okay, so if n is even and a is greater than 0, so here's the function, a, b to the n, and we can call it any of these things. It's all the same. but we're just going to go with ab to the n for our examples here. So if a is a positive number, then we're looking at a positive power function. And if n is even, then we know we're looking at something that resembles a parabola, right? That's a power function. That's the leading term is the power function. So when we think of the graph, okay, so here's the graph of the function. We don't know what's going on in this middle part, right? We don't know what's going on near the origin. But somewhere, eventually, if this is an even function, it's going to be going up and up. We know that. Okay, that's the nature of an even power function that's positive. Now, if we have an even power function that starts with a negative number, then we know that that one, and then again, we're only talking about the ends, not the middle part. We know that this one will eventually be going down. Now, it doesn't really matter where we start this. I don't care where we start it here. What I care is that it's going to be going down. Now, they're both going down because this is an even function. This is like an even power function. So remember, these all resemble parabolas, right? Okay, so in this first case, what we're actually saying here is that as x goes towards infinity, so as x goes this way, f of x will go towards positive infinity. So as x goes towards positive infinity, f of x goes towards positive infinity. As x goes towards negative infinity, so in other words, when it's moving this way, the function's also going up. So as x goes towards negative infinity, f of x goes still towards positive infinity. That's the case, again, with the even positive power function. All right, let's try the same thing for this one. Let's just write these out. Okay, so in the case of a downward even power function, which resembles a parabola, a negative parabola, as x goes towards positive infinity, the function's moving down. So that's what I have written right here. As x goes towards positive infinity, f of x is going towards negative infinity. And as x goes towards negative infinity, so is the function going down. So I have as x goes towards negative infinity, f of x goes towards negative infinity. So we've got the four situations here. Let's see if we can fill out the other two. Okay, I'm going to pause the video, see if you can draw these and fill out the other two. I'll pause it and then I'll show you the drawings, and then we'll go ahead and write in the x approaching infinity statements. Okay, so there they are. So just in case there's any confusion here, if n is odd and a is greater than 0, we might have, for example, f of x equals, let's say, a greater. So how about 2x to the third, something like that. Well, we know 2x to the third resembles, well, we know what that looks like. It's just it's a parent function. So it goes up here, it goes down here. Now, the only difference is in this, we're not focused on the middle. We're only focused on the first term. So we're not focused on the entire, if this is the entire function, that's what the graph looks like. But with polynomial functions, there could be a lot of turning points, local maxes and mins in between here. But in the ends, that's what the power function is determining, what's happening at the greatest and the least possible values here. And we know over here, an example of this one would be something like, let's see, n is odd but a is less than 0. That might be something like f of x equals, how about, let's negative 3x to the fifth, for example. And we know that power function has the general shape that goes a reflection of the other one, right? So it's something like this. It goes down this way, so it's something like this. Right? They're all similar to the cube root, or to the cube power function. So we know that's the general shape. So, but we don't know what's going on in the middle with the polynomial functions. So we leave that middle as sort of like, we'll figure that part out later. And that's what we're doing here. Okay, so let me write the x approaching infinity statements. You guys can try the same thing. Okay, and so there, as we can see, as x goes towards positive infinity, f of x goes up. So there they are. As x goes towards negative infinity, f of x goes down. And then over here, we've got the opposite. Okay? Now, what we're going to do next is we're going to fill in the examples on the bottom here, and then we're going to see if we can answer these. Okay, so this is just these examples that we already did on the other side, and there they all are. Now, I wrote for the first one that n is an odd number and a is less than 0. Let's fill those in for the rest. Okay, there they are. Now I'm going to fill in a quick sketch of each. Okay, and now the statements.